Planet Earth, a swirling blue sphere in the vastness of space, harbors many secrets beneath its surface. Understanding Earth's layers is crucial to comprehending the planet's history, its dynamic processes, and ultimately, our place within its intricate system. Just like peeling back the layers of an onion, each layer of Earth reveals a unique story, offering clues about its formation and evolution over billions of years. The Earth's crust is the outermost layer, the ground beneath our feet. It is the solid shell on which all life exists, providing the foundation for our ecosystems and human civilization. It is surprisingly thin, like the skin of an apple compared to the whole fruit. Just as the apple's skin is delicate and easily damaged, so too is the Earth's crust, vulnerable to both natural and human-induced changes. The crust is composed of two types: oceanic crust, found under the oceans, and continental crust, which forms our continents. Each type has unique characteristics and plays a distinct role in the Earth's geology. Oceanic crust is denser, made up of basalt, a dark, fine-grained volcanic rock. This density allows it to sink below the lighter continental crust at convergent boundaries, leading to subduction zones. While continental crust is lighter, composed primarily of granite, a coarse-grained igneous rock. This lighter composition allows it to float higher on the mantle, forming the continents and towering mountain ranges. This difference in density plays a crucial role in the dynamic processes of plate tectonics. The interaction between these two types of crust drives the movement of tectonic plates, shaping the Earth's surface over millions of years. The crust is broken into several large pieces called tectonic plates. These plates fit together like a jigsaw puzzle, covering the entire surface of the Earth. These plates are in constant motion, albeit very slow, moving a few centimeters per year. This movement is driven by the heat from the Earth's interior, causing convection currents in the semi-fluid asthenosphere beneath the crust. This movement, driven by the heat from the Earth's interior, is responsible for earthquakes, volcanic eruptions, and the formation of mountain ranges. These geological activities are a testament to the dynamic nature of our planet, constantly reshaping its surface and creating new landforms. Understanding these processes helps us appreciate the delicate balance that sustains life on Earth and the importance of protecting our fragile home. Beneath the crust lies the mantle, Earth's thickest layer, extending down to a depth of 2,900 kilometers. The mantle is primarily composed of silicate rocks rich in iron and magnesium. Unlike the brittle crust, the mantle behaves like a very viscous fluid over geological timescales. Heat from the Earth's core drives convection currents within the mantle. Hotter, less dense material rises while cooler, denser material sinks. This continuous churning motion acts like a giant conveyor belt, dragging the tectonic plates along with it. The mantle plays a crucial role in Earth's geology, driving the movement of continents and shaping the planet's surface. Deeper still, at a depth of 2,900 to 5,100 kilometers, lies the outer core. Unlike the solid mantle, the outer core is composed of liquid iron and nickel. The extreme temperatures and pressures at this depth cause the metals to exist in a molten state. The liquid iron in the outer core is in constant motion, generating electric currents. These electric currents, in turn, produce a magnetic field that surrounds Earth. This magnetic field, known as the magnetosphere, acts as a protective shield, deflecting harmful solar wind and cosmic radiation, making life on Earth possible. The inner core, a solid mystery. At the very center of the Earth, from 5,100 to 6,370 kilometers deep, lies the inner core. This region is one of the most inaccessible and least understood parts of our planet. Scientists have long been fascinated by what lies beneath the Earth's crust, and the inner core is a key area of interest. Despite the intense heat, estimated to be over 5,000 degrees Celsius, the inner core is a solid ball of iron and nickel. This temperature is comparable to the surface of the Sun, yet the inner core remains solid. The reason for this lies in the extreme conditions found at such depths. The immense pressure at this depth forces the atoms to pack tightly together, giving the inner core its solid state. The pressure is so great that it overcomes the natural tendency of iron and nickel to melt at such high temperatures. This phenomenon is a subject of extensive research and continues to intrigue geophysicists. The inner core plays a crucial role in the Earth's magnetic field. The solid inner core, along with the liquid outer core, creates a dynamo effect that generates the magnetic field. This magnetic field is essential for life on Earth as it protects the planet from harmful solar radiation. The heat flowing from the inner core to the outer core helps drive the convection currents responsible for generating the magnetic field. These convection currents are created by the movement of molten iron and nickel in the outer core, which is influenced by the heat emanating from the inner core. However, the inner core remains a mysterious realm, with much about its composition and behavior still unknown. Scientists use seismic waves generated by earthquakes to study the inner core, but many questions remain unanswered. What exactly is the composition of the inner core? How does it interact with the rest of the Earth's layers? These are just some of the mysteries that continue to puzzle researchers. The inner core is a frontier of scientific discovery, holding secrets that could unlock new understanding of our planet's history and dynamics. Plate tectonics, a dance of continents. This intricate ballet of colossal landmasses has shaped the face of our planet for billions of years. The theory of plate tectonics revolutionized our understanding of Earth's geology. It provided a framework to explain the dynamic nature of our planet's surface, which is constantly changing and evolving. It explains how the continents have drifted over millions of years, breaking apart and colliding to form new landmasses. This process, known as continental drift, has led to the formation and reformation of supercontinents like Pangaea. The movement of these plates is responsible for the creation of mountain ranges, ocean basins, and the distribution of volcanoes and earthquakes. These geological features are a direct result of the immense forces at play beneath the Earth's crust. The interaction between tectonic plates creates zones of intense geological activity. These zones are hotspots for natural phenomena that can dramatically alter the landscape. At convergent boundaries where plates collide, mountain ranges like the Himalayas are formed, and volcanic eruptions occur. The immense pressure and friction at these boundaries can push the Earth's crust upwards, creating towering peaks. At divergent boundaries, where plates move apart, new crust is generated, forming mid-ocean ridges. These underwater mountain ranges are sites of continuous volcanic activity, where magma rises to create new oceanic crust. Transform boundaries, where plates slide past each other, are responsible for powerful earthquakes like those along the San Andreas Fault. The grinding motion of these plates can release enormous amounts of energy, leading to devastating seismic events. Understanding plate tectonics is crucial for comprehending the Earth's past, present, and future. It helps scientists predict geological events and understand the distribution of natural resources. This knowledge is essential for preparing for natural disasters and managing Earth's resources sustainably. As we look to the future, the dance of continents will continue to shape our world. Scientists use models to predict how continents will move and interact, offering a glimpse into the Earth's ever-changing landscape. The story of plate tectonics is a testament to the dynamic and interconnected nature of our planet. Volcanic fury, windows to Earth's interior. Volcanoes, while potentially destructive, offer valuable insights into Earth's interior. Volcanic eruptions bring molten rock, ash, and gases from deep within the Earth to the surface. By studying the composition of these materials, scientists can learn about the temperature, pressure, and composition of the mantle and even the deeper layers. Volcanoes are often found along plate boundaries where the movement of tectonic plates creates weak spots in the crust. However, some volcanoes, known as hotspots, occur in the middle of tectonic plates. These hotspots are thought to be caused by plumes of hot material rising from deep within the mantle, creating volcanic activity at the surface. Seismic waves, listening to Earth's heartbeat. Earthquakes, while often devastating, provide valuable information about Earth's internal structure. When an earthquake occurs, it releases energy in the form of seismic waves that travel through the Earth. By studying the speed and direction of these waves, scientists can map out the different layers of the Earth, much like using ultrasound to see inside the human body. Different types of seismic waves travel at different speeds through different materials. By analyzing the arrival times and patterns of these waves at seismic stations around the world, scientists can determine the thickness, density, and composition of Earth's layers. This technique has been instrumental in revealing the existence and properties of the Earth's core. Conclusion: unraveling the mysteries within. Understanding Earth's layers is not merely an academic exercise. It has profound implications for our understanding of the planet's history, its dynamic processes, and the very forces that shape our world. By studying Earth's interior, we gain insights into the formation of continents, the mechanisms of earthquakes and volcanoes, and the generation of Earth's protective magnetic field. As technology advances, scientists continue to develop new tools and techniques to probe deeper into Earth's interior. Future research promises to unravel further mysteries about the Earth's core, the dynamics of the mantle, and the intricate interplay between Earth's layers that make our planet a unique and habitable world.